So grab out your sheets. The page I'm looking at, guys, you have a exercise 17, centripetal force, and talks about centripetal force. Please realise that centripetal force is the force that is pointing inwards towards the centre of motion when things are going in a circle, right? It doesn't balance anything. It's actually a description of the force which keep things accelerating and going in a circle. The only reason that when we did the centripetal force equals the gravitational force, when we did the experiment, of course, we were imparting motion to something in a horizontal plane, and it was being equalled by the gravitational force downwards. But in general terms, the centripetal force in the same direction as the gravity and all that stuff, right? Yep. I'm just going to read it and I'm going to give it to you. So exercise 17 says this. When the space shuttle is in a stable orbit around the Earth, it is actually falling towards the Earth all the time. The result is that it follows a curved path, the orbital path. Because its direction of travel is always changing, a force must be acting on it. The force involved in causing any object to move in a circular path is called a centripetal force. Without a centripetal force, objects travelling in a circular path would move in a straight path. Who tells us that? No, he doesn't. Newton. What does Newton tell us?
A lot of things.
Everything stays in constant motion unless acted on by an unbalanced external force, right? So, and business guys, this is A, recorded, but B, I need to be able to talk over you, so either whisper or don't talk. I appreciate that, okay? Right, so if you see an acceleration, there's going to be a force. If there's no force, something just keeps going in constant motion. Constant motion might be sitting on a desk not going anywhere, or it might be something just drifting off into space. If there's no change in motion, there's no force. If there's a change in motion, there's an acceleration, there's a force. Going in a curve, there's a change in motion, there's a force. Okay? That's Newton's first law. Then there's some pictures of various ways you can see centripetal forces in page 17. So, Riley, what's the first one?
Riley.
This Riley will do. Wrong sheet. Exercise 17. What's the first thing they're showing there?
String tension.
Yeah, string tension. That was what we're doing with our orbiting piece of rubber cork the other day. You have the road friction with the car going around. Brad, what's the third picture of?
Third picture.
Yeah.
You mean the ones down the bottom?
The ones in the middle, right there.
Oh, right.
Yes, what's that?
So it's probably something to do with the battery.
Good reasoning.
It's, yeah.
What's the symbol? It's positive and negative. It's got a Q there.
Let's just say it's something to do with that.
Something like that. It's a charge.
Yeah.
So it's something to do with two charges, one circulating around the other. The next one, Tom, is gravity. So satellite going around something. And the last one's really easy because they actually tell you. Magnetic force. So we use a calculation to calculate the centripetal force acting on an object, and then that you can get the equation for the centripetal acceleration. Okay? Now, centripetal force, what formula is it?
FC equals mv squared on R.
That's a very interesting. But we know on this side, it's a force. Newton's second law says a force is
F
ma, and that side is still mv squared on r, and that m there disappears from there. So it's how you get v squared on r is the centripetal acceleration, the acceleration that causes it going to curve.
So how can you use FC equals mv squared on R when the velocity of an object and that motion is always changing?
Okay, that was different. Okay. The answer is, for us, it's a centripetal velocity, or an angular velocity. But actually, what you're measuring is the instantaneous velocity. So at
So
that,
you're not measuring the average velocity as opposed to that, you're measuring the velocity of one
Yeah, but remember, for something going in a circle like this, if you looked at its instantaneous velocity there, and its instantaneous velocity there, and its instantaneous velocity here, the magnitude of it, under most of the circumstances, is the same. So as we're in circular motion, the number we need is the magnitude of the velocity, not the direction. We just understand that it's constantly changing. If you need to analyse the direction, you need some much more complicated maths that we don't do. You have to use angular momentums and angular measures. So you measure motion. We used to do this in high school. Instead of measuring things in metres per second, you measure them in radians per second, and all that stuff. Yeah. Okay. So this here is a simple picture of an idea of someone is swinging a ball around on a rope or something. You've got a stroboscope going, which is flashing at a regular rate, right? So every time it flashes, you see it, and you can get a picture of it. It shows its path around the circle, and we're given some information. All right. So we're given a linear speed, and we're given a frequency of 24 hertz. 24 flashes in a second. Okay. So what you've got here, well, the first thing, calculate the period of rotation of the object. How long does it take to make one circuit of this circle? How many flashes? That's a good question. So you got a starting one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Might need to calibrate it. So you got 14 flashes out of 24 per second.
Is that diagram after 1 second?
No, you get 24 flashes per second. It's 24 hertz. Hertz means how many flashes per second. So there's 14 flashes, which means to go from there to there to 14 out of a possible 24 for 1 second. So it's 14 24ths of a second to go from there to there. Okay?
582.
So the time frame it took for this picture was 0.583 or 2? 3 of a second. You were. Okay.
Like honestly, what is your thought process to work out that 14 on 24 without a calculator with 0.05, 0.583?
If it's 0.6, it's going to be 14.4. So it's less than 6.6.
Yeah, how do you know that?
Well, I use it as fractions. 10% of 24 is going to be 2.4, and 12's half. So that'd be 14.4. It's going to be 60 or 6.6. So I guess it's going to be roughly 0.58.
It's good estimation skills. That's exactly what you need there.
Isn't it an estimation? It's always dead on.
Some of the other ones that you do.
Okay, so what's the next step to work this out, Jerry? You're trying to work out how long it takes for it to go from there all the way around and back to where it started. How long will it take?
Well, we need the radius up. We find the radius of the
What strategy can you bring to try and solve this? You're sitting in an exam, you're asked this question, what are you going to do? How long does it take for it to go all the way around the circle?
Well, only 14, you only said 14 times.
Have you got the radius of it?
No?
Couldn't you just like, because it's a little bit over halfway. If you take 1 off 13 and just double 13 and say it's 26.
Because once you get the amount of rotation, once you get the amount of flashes it does for a complete rotation, you get the speed, and then you can get the period, and then you can.
Yeah, so how are you going to do it? What ideas do you have?
Is it saying the stroboscope, linear speed is 20 meters a second, and the stroboscope does 24 hertz? Is it saying in 24 hertz it's going to go all the way around, or we're not sure?
No, they're not. We don't know.
Saying 24
Well, linear
hertz,
speed of 24
it flashes 24 times in 1 second.
Yes, we know that. So once it's going to be 24 flashes, what are you going to do to solve this?
Oh, yeah. Couldn't you just use the formula
Centripetal Force.
formula and just like try and find the rest of the values?
Well, we don't have the velocity. Oh, we do have.
You do have a velocity. And you do
But we
have
don't
a
have-
I don't
weight.
understand what's happening in
We
there.
don't have the centripetal force. We don't have radius. So, you've got
So
the one
there's
right
a spin and spinning.
You've got a ball or something on the end of a string. It's spinning it around, and it's got a camera which just takes photos of it, on one frame. And they've got a light flashing. The light flashes at 24 times in a second. So they opened up the camera, they took that photo, which means because the light,
They're spinning in the dark.
yeah.
Oh, light stuff.
So there's a light flashing on and off. It's the old-fashioned way of doing it. You don't see too many of them anymore because of the new modern technology. But
You can't do this centripetal law thing because you've got two unknowns that are all equations in one.
yeah,
You don't know the centripetal force. You don't know the radius.
I don't know what where the stroke light is.
Oh, we can go show.
okay, you're stuck to some degree. What's the simplest thing you could possibly do?
The amount of possible.
You could, or
Measure the distance between and keep going.
1, that's interesting. 2, could do this. 3,
That's not accurate though. So.
I didn't say it was going to be perfectly accurate. 1. Oh, I can do that. I'm pretty impressed.
Recalibrate your dog.
1, 2, 3, 4, 5, 6, 7, 8, 9, about 10 more. 24.
Seconds of a full revolution. So what's the max way to figure it out?
Right?
Yeah, what's the math?
Sometimes there isn't a max way to figure things out. Sometimes you get enough information.
If I take 2 off either side, it's like halfway, so it's going to be a second.
Yeah, that did work too. But it works out as being a second for the period. Sometimes that's what you have to do. You have to use the diagram. Yes, it would. Okay.
That's Kepler's law.
So the frequency of rotation.
124. 124.
Yeah.
Or if it's 24
So
times,
the
20
frequency
minutes.
is 24 hertz.
It's just 24.
Okay, 24 times in 1 second.
No, it doesn't.
It goes 1
That's
in
the
1 second.
goes 1 in 1 second. It's 1 hertz is the frequency.
Oh, the frequency of the period. Oh, okay.
Calculate the radius now. Can we do that?
Yes, Newton's modified Kepler's third law. We've got everything but the radius.
Use Kepler's law.
R cubed over c squared equals gm over 4 pi squared. That's what I think.
Or we could use the speed and our meters seconds. V is 2 pi r on t. So you've got the period and you've got velocity. And you just want to work out.
So what you're saying is you've got 2 pi r on the period equals 20 velocity, which is correct. Good. So then to find out r, it's just going to be r is going to be 2 pi. Sorry, no, it's not. It's going to be.
What formula did you use to get that? Like, how did you get the 2
Okay. I did calibrate a moment. Velocity equals distance travelled or displacement over time.
Yeah.
So the displacement that you travel is 2 pi r, that's around the circle, and the time is the period of rotation. And from that, we want to find that. We know v, we know the period. So if you rearrange, r is going to be the velocity times the period divided by 2 pi, isn't it? And you can work that out easily enough with a calculator, or you use Riley. If you don't have a calculator available, you do a Riley. Just 20 times 1, that's easy, divided by 2 pi.
3.4.
And that gives you that.
What does that give us?
That gives you the radius. Once you've got the radius, the next question is calculate the centripetal force. Now the centripetal force, what was the answer, please? 3 point. And the centripetal force, well, that's just simply plug and chug maths. You get the centripetal force equals mv squared on r, which is going to be the mass, which we said was 2 kilograms times, not 20, 20 squared, mv squared on r, which is the 3.18, which will give you
220. No.
sorry?
20 squared.
Yep, 20 squared because it's v squared.
V times 40.
It's going to be 30.
251.57.
Now, guys,
Yeah, 200.
not much.
I was only up by 11.
Okay, guys. The trick in this question, and it's something that happens sometimes in physics papers, is using the diagram. If you don't use the diagram, you don't solve the problem. Now, very often the HSC paper, they will put a diagram in. Sometimes it's just there to fill in space and it just backs up what's in the writing. But there are times when you just have to directly measure stuff off the diagram. What's normally the hint to doing that, do you reckon? Yeah. So, yeah. So if you see a diagram, in the paper and it says drawn to scale, there's probably a really, really good reason it's in there drawn to scale. You probably need to actually get information directly off that diagram. The other place students tend not to look very often is graphs. They don't get the information that's available to them in graphs.
Oh, they're a bit violent, so that's too graphic.
Yes, absolutely. They should be M-rated. But if you have a graph, so you have something like that, right? And it starts off at 0, it goes to 10, and it goes up to 50 newtons. And you have something does that, 50 meters per second. And they ask you a question which says, you have an 8 kilogram mass, find the force acting on it. A lot of students would look at that, shrug their shoulders and go away, but there's the reason there's a VT graph in it. To get the acceleration of it, slope of the line, right? So it's, yeah, so it's about, I mean, I've drawn it roughly, but if you see a diagram in a question that says drawn to scale, don't don't just ignore the picture. It might be that that diagram is really vital to give you the information to solve it. If there's a graph in there, often the graph has information in it that you need to solve a problem. And don't forget, very often what they will get you to do in the HSC is they'll get you to draw a graph, and then they'll get you to extrapolate it. Do you know what extrapolate means? Okay. Yep. Oh, that's different. So there's your graph. So what you might do is you might have some data that does this, and then they ask you to predict what will happen at 15. That's extrapolate. So it says extrapolate the information to determine the velocity at 15 seconds. Yeah. So extrapolation will be to continue the curve on. Okay? They will have a range of answers written down that I expect you to work out. And one of the difficulties can be if they give you something that looks a bit like this, they give you some data and they ask you to draw in a line of best fit. Now, there are errors people make all the time when they look at lines of best fit. People have to be aware of it. Here's the first one. Okay, this is something people often do with this sort of thing. Is that a line of best fit? No. That might be.
No.
Isn't. Actually, you're dead right, it's not. But putting that through there, not zero is better. There was one the other a couple of years back where they had a line of best fit, and everyone who put it through zero got zero for their result. Where should that line of best fit go? About there? Because it's got about as many above as below, and it works out reasonably well that way. The other thing, or could it be this? No, it couldn't be that.
Line of best fit has to be a straight line, though, doesn't it?
In that one it is, it would be, yeah. And you have to make a judgment about, a line of best fit doesn't mean necessarily straight line, it can be curved. You have to be really careful, but what you're looking for is you're looking for data points, as many above as below, and about equally spread, and you use a clear ruler. Okay, really important. So it's pretty much the average. Let's get rid of that one. Get rid of that. Yeah.
The graph's supposed to be linear and you just use a straight line, or it's like supposed to be like parabolic.
Yep. What happens if you have one like this, guys?
Then that's an outline. Nothing.
Thank you, it's an outlier, ignore it. So if you get an odd cross up there, just take it out of the picture, put your line best fit in. Yeah, the line's not going to be this one. It's unlikely to be.
Yeah, it's going to be that.
Yeah, that's right. You can do that. So it's important to be able to interpret your data and use it correctly and use what's in front of you. Okay, next question. Yeah, that's useful. I'm sorry they're so slow for you. I'm just trying to help you answer questions to the HSC. Right. Identify the data that's really important up in this question. Right. Okay. And what are you asked to do?
Find acceleration. Between the road and the truck. Also define the centripetal
Yep.
there highlighted.
Yep. You can go in, you can highlight your paper like that if you like, although I'd use smaller writing. Okay, yes. Okay, when you're driving with a... Yeah, when you're going on a road, hopefully it's flat and you want to turn flat, so you have to have a sideways force acting on you. What force is it turns the car? It's friction between the tyre and the wheel, so sideways friction is what you want. Otherwise you're driving on a wall.
Maybe if you're driving.
Priuses don't fall over, they're too low to the ground. Okay, so
No. They're just depressing.
all right. So the first thing in working this out is you've identified the data and things you need to do. When you write your data down, okay, what data do we need to work out the force on it?
Mass and acceleration.
No. Because what shape is this thing going in?
Circle.
Circle. Which formula are you going to use? This one. All right.
Calibration, though.
I had calibrators gone crazy on me. All right. So the first thing we want to do is we need to work out a mass. What is this thing's mass? 2,000 kg. Yep, that's your first step. Every time convert it back to kilograms, meters, and seconds. Okay, now your velocity isn't... Okay. And you have a radius of what? So, given that, what am I going to do with this, Jason?
Plug and chug.
It's a plug and chug question, isn't it? So, I'll just chuck the numbers in. So, M, of course, is 2,000. V is the 12 squared. And R is 150. And I'm not going to bother working that out, but that's how you do it. It's that simple. Now, when you want to work out the...
282,000 over 180.
What was it?
1,900.
And when you write that down, what are you going to put after it? I'm not.
Newtons.
Newtons, because it's a Newtons question. Okay. Going to ask you to find out the centripetal acceleration. So, Josh, what do I have to do to that answer to get my centripetal acceleration? So I've got the centripetal force acting on it, or the friction force. What do I have to do to that to get the centripetal acceleration? Remembering, Rich, if F equals ma, and I want A, divide by M, which is 2,000. Which is 0.98, is it? Okay.
0.96.
The next question is very, very similar. I don't really need to keep doing these for you because you can see how you approach them, what you do with them, yeah? Kepler's law, yeah. Who is this Kepler bloke? I don't know Kepler.
There's only one else. I don't know where you get Kepler. It's not.
You say it in half, I'll say it again. So, like, you say it first time.
Okay.
Yeah.
Look.
Look.
No, 5 times 5.
Calculate.
No, 5 times 5.
Maybe it's don't calculate.
K-A-L-A.
There's no L in his name.
Are you serious? That's why it's called
There's an L in his name.
No, there's nothing else.
Okay.
Eyesight. Right.
That's the kelp from Kepler's law. Okay.
Someone never wants to talk
Okay, guys. Right, Jason, you can help me out with this one because you love doing it so much.
Yeah, of course.
All right, first question.
Calculate the orbital period with its average distance from the 106,600.
So the first thing you're going to do, of course, is you're going to work out your data.
Takes 23 hours and 56 minutes to come into orbit. Done. Don't have to work that.
Let's just prove that you're right. So Jason, what do we know from this?
Well, we've
Look
got the
that up.
diameter, so diameter, because we have a diameter, we also have a radius, it's got a half it, and then we also have the distance to that multiplied interesting.
Okay. So
So there's
that didn't change for some reason.
Yeah, I mean, what's so interesting on that photo?
All right. So Jason, here's the formula we've been given. In that, let's start on the right-hand side of it. Which things do we know in this formula?
Nothing.
Do we know big G?
Gravity, something.
It's the gravitational constant. We know that.
6.6.
Do we know the mass of the Earth?
Yes.
Good. I'll give it to you if you don't. Do we know what 4 pi squared would be?
Yes.
Yes, that's all okay. Do we have a...
Radius, yeah. That's
Roughly about
Oh, sorry,
6.6.
we don't need mass of Earth. Sorry, I'm going silly. We need the mass of the Sun, don't we? Oh, no, it's going around the Earth. Sorry, no, it is mass Earth. What do we have? Do we have a radius?
Yes.
And what do we want to find out? We want to find the orbital period. So basically, it's T.
Yeah.
So we're just going to that formula, putting the numbers in, rearranging it, getting the numbers out.
So we'd have to... T,
Yes, I can.
T,
So let's rearrange that. I'll do question 2. That's me growling. That should be that. Okay. So, where I am, I'm just getting all right, so what's the formula that I have to rearrange? So R cubed
G is supposed to be bigger than the M.
doesn't matter in this case really. Okay, so the first thing I'm going to do is I'm going to take this T squared and I'm going to move it to this side. So I'm going to end up with R cubed equals T squared G M on 4 pi. Then what I can do, Marnie, is I want to take the, I want to get the, it's got the T squared there.
Pi squared.
Ah. So I want to take the 4 pi squared, I'm going to take this side, because it's a division, it becomes a multiplication on the other side. So it becomes 4 pi squared R cubed. I've got to divide by GM equals t squared. Now to get rid of the squared, that just becomes a square root and that side of it.
I can't work that out.
So are you trying to, which one are you trying to figure out?
I'm trying to work out the period for the moon.
Cube root.
No, that's the squared one. The r is cubed.
Oh.
Now, from our data that we had, okay, let's go put the data in and then you can calculate it. So what is the radius of the orbit?
Half 3, 4, 6, 7.
Half of 3, 4, 6, 7.
Half.
I think it was 3, 4, 6, 7.
Half a lot.
Yeah, 3, 4, 6, 7.
Oh, that's so different.
On 2,
Mostly half a lot.
823.
3.5.
1,733.5 kilometers.
Oh, 781, okay.
Mass of the Earth is 5.98 times 10 to the 24 kg.
So you need 10 to the 3 on the 1733. 1,700, because that's in kilometers, so you need 10 to the 3.
To make it meters, yep, correct. And what else do we need to solve this? Nothing. So we substitute in square root 4 pi squared times 1733.5 times 10 to the 3, and all that is cubed all over 6.67
Go for it.
Yes, numbers and letters. Yes, Marnie. Squared. Yeah. When you square it,
So is that 5.98 times 10 to the 22?
5.98 times 10 to 24. So what you're asking is when I square it over it. You're saying? Lunchtime I'll go through it with you. Just make sure.
You didn't even get 23.
What is it?
I got 780. You didn't even get one of the numbers.
718 point what?
Does that work out?
Oh, you got the 7. Oh, yeah. 718.05 rounded.
Oh, is that minutes?
Must-
Oh, wait.
that can't be
You
right.
have to in, oh, wait.
You're wrong.
What do I have to do it? Because that's in seconds.
It can't be 718.85 seconds.
Yeah, that doesn't make any sense.
That doesn't make any sense whatsoever.
Must be wrong.
You must be wrong. I'll put the calculator off.
That's 100.
I squared.
4 pi squared times
Did you put the square root?
1733.5 times 10 to the 3, all cubed.
Yeah. 6.67 times 10 to the negative 11.
Yep. Times.
5.98 times 10 to the 24.
Yeah. And what do you get?
Did you put the square root there?
Yeah, I did. It's pi squared, isn't it?
4 pi.
Sir,
Is it 10 to the minus 11?
Yeah. Let me draw it in big writing so you can see what you're doing. And hopefully it will be calibrated. So it'll be the square root of 4
What? Doesn't be like 86,000.
That's so you can read it. Unless I've got the formula rearranged incorrectly.
If you're all doing that calculation, there's nothing wrong with that calculation. There's something wrong with the way you've rearranged it.
Could be.
Yeah, right, you've got 10 to the negative 1. See, now yours gets the same answer.
Go back to it.
Yeah, no, that's right. Taking a long time to work this one out.
I think you got the same one and nobody else calculated. Because he used 10 to the negative 13.
It can't be 786.
Yeah, I got that.
It's not 786 for the moon to orbit around the Earth. That's what it means. That's what it's saying.
Oh, this is the one without the calculator. Oh. I'll go back over the calculations in the break and come back to it. Jack wanted me to quickly look at another question, which we'll do. We don't have a lot of time. Question 2.
Can we maybe look at it tomorrow? We have no time.
Let me start with it and then we'll go back. All right. This, guys, question 2.
Group mentality packs up and everybody else.
Okay, just watching, guys, because I'll tell you what the trick with this one is. What they've done is you've got the sun, you've got the Earth, and you've got a distance between them. And they're giving you the diameter of the sun and the diameter of the Earth. So what you have to do is you have to take the radius there and the radius there, add them onto that, and then just use the formula. Yeah.
86,000.
Okay.
In my